Now that you know about complex numbers and how to work with complex numbers, and you know a little bit about the natural exponent, or e to the x, you are ready to learn the complex roots of unity. Now, this sounds like a really bizarre, kind of magical, mysterious term. So what is the roots of unity? Maybe you think that this is something from a fantasy book, like there's this special magical tree in the land of unity and its roots have magical powers or something like that. But actually the roots of unity turn out to be a relatively tame concept in mathematics, but also really important for example, the Fourier transform and other aspects of signal processing. And once you learn about the roots of unity algebraically, then I will introduce you to plotting and graphing the roots of unity, and that will lead to a really beautiful plot in Python. I think by the end of this video, you will see a nice example of the intersection between math and art. All right, so let's get started. So the roots of unity essentially just means that for some number z, which is a complex number, so a complex valued number z, if you raise it to the nth power, then it equals 1. Now, on the one hand, if you set n to be 0, then this is a trivial equation because any number to the power of 0 is equal to 1. But if n is a larger number than 0, let's say if n is 5, then it's not so obvious what z should be in order to get z to the nth power to also be equal to 1 when n is equal to 5. But it turns out that the solution, the way to define z, is according to this formula. So z equals the natural exponent, so e to the power of, and this whole expression is in the exponent of e, and that is 2 pi I k divided by n. So pi is the number 3.14 and so on. You see pi all over the place with circles. I, of course, is the imaginary operator, or the square root of -1. And k is a set of numbers that goes from 0 to n minus 1. So if n is 5, then k would be 0, 1, 2, 3, 4. So then the idea is that for each value of k, you put k into this formula, that gives you a z, and then you take z to the nth power, and that will give you the number 1. And because k is defined as 0 up to n minus 1, then that means when n equals 5, then there are 5 roots of 1. So in other words, for z to the n, there are n nth roots. Okay, so what I'm going to do now is switch to Python. I will show you how to demonstrate this algebraically, so just with numbers, and then I'll show you how to make a plot that visualizes these complex roots of unity, and that will lead naturally into the exercise. In this video, we are going to be using several modules, including NumPy, SymPy, matplotlib.pyplot, and the functions display and math from the ipython.display module. Okay, so let's begin, and actually let's begin with n equals 5, since that's the number I was talking about in the slides. So what I'm going to do here is loop through for k in range 0 to n, and then what I'm going to do is compute the nth order, or I should say the kth root of 1, and then print that out, and hopefully we will see that that equals the number 1. So let's call this the root, so I'll call this variable root. So that was numpy.exp, and then we have 2 times pi, so numpy.py, times the imaginary operator, which I'm writing as 1j here, times k, and then divided by n. And now actually I'm even just going to run this cell already. It's not going to print out anything, but it also didn't give me any error messages, so that's a good sign. Okay, and now I'm just going to print out the root. So this does not seem to correspond to the number 1. None of these is the number 1. So what's going on? Actually, what's going on is that this is not yet the nth root. This is that number. Maybe I should have called it z, and maybe it would have been a bit clearer. So remember from the slides that once you put k into this natural exponent, you then need to raise z to the power of n. So let's try this again like this. Okay, so maybe you think this still looks a little bit confusing, but let's go through each of these numbers in turn. So this first number is 1 plus 0j, so that's really just the number 1, so we get confirmation there. How about here? This is almost the number 1, it's 0.999999, so it's almost the number 1. And then this is a complex number, so the imaginary part looks like it's minus 1j, but actually you have to notice this scientific notation here, e to the minus 16. So this is actually basically just 0 plus computer rounding error. And if you look down at these other ones, you'll see this is 1, and then also a really, really, really tiny number. So this is basically a decimal point and then 16 zeros after that before you start getting to some non-zero numbers. Same business for all of these guys. Now, the reason why we are not getting exactly 1 and why there's a tiny, tiny imaginary component here is essentially because of how this number pi is computed. This is not actually the real pi. This is just pi estimated out to some number of digits. So what I think we can do instead is use the SymPy toolbox or the SymPy module in order to get pi and also e in terms of symbols, not in terms of estimated numbers. So now I'm basically just going to convert everything into SymPy. So sim.exp, this is going to be sim.pi, and here I'm going to use sim.i instead of ij. And now let's see what happens. Aha! Now we get all ones. Okay, so this is looking good. And now the last thing I want to do in this cell is just make this look a little bit nicer. So let's say display math. And then what I want to do is basically say e to the power of all this stuff raised to the nth power gives us the number 1. So let's see, that'll be %s, oops, I need it in quotes here, %s, and then I'll have a large right arrow. This leads to %s, so now we need to do our substitution. So this first one is going to be sim.latex z, and then the second substitution is going to be sim.latex z to the power of n. Okay, so this is looking a little bit better, except it's actually not totally accurate, and that's because I made a little typo here. Or maybe I made it here. Anyway, the point is this is not actually correct. What we need to do is say z to the power of n. So I'm going to put parentheses around here, and then caret, and then another %s, and then here I'm going to need n. Okay, so this number in here is the number z, and then we raise that to the 5th power, and then we get 1. All right, so that is pretty neat, and then it's worth checking that this works for other numbers as well. So here are the 7 seventh roots of unity, and we can do 17, so these are the 17 17th roots of unity. And actually now we've discovered a bug, and I didn't even realize that this was there. So notice now the 1 is in the superscript and the 7 is not in the superscript. So in fact, this needs to be in curly brackets like this. All right, this is looking better. Okay, now we could do this, all day, go down to this, but that's going to end up just taking a really long time and making lots and lots of printouts. So let's keep this at, how about 4? So this is already kind of interesting. You see that the 4 fourth roots of unity are 1 and then I and then -1 and -i. And that is a good segue into what I want to show you next, which is plotting these roots. Now z is a complex number, so that means that we can plot this complex number on a circle, on a unit circle, just like I showed you in previous videos with graphing complex numbers. So let's do that down here. Let's say n equals 4. And now essentially what I'm going to do is repeat some of this code, but I'm going to display it instead of printing it out. So I will even copy and paste. So here we compute the kth root of unity, and then I'm going to plot it. So how do we want to plot this? So I want this to be a line that goes from the origin to this complex number here. So you will recall we need to specify the x coordinates and then 2 y coordinates. And we start at coordinate x equals 0 and y equals 0. And then we go up to x equals the real part of z, and y goes up to the imaginary part of z. All right, so let's already run this and see what happens. So we start getting some error messages. And this is actually related to some interactions between SymPy and NumPy. So what I'm going to do is convert all of these back from symbols into numbers. So numpy.exp, numpy.py, and here this will go back to 1j. Okay, so this is pretty funny. We get a plus sign where each of the arms have a different color. And in fact, these correspond to these 4 numbers up here. So up here, the first root of unity is 1, which you see here, and then it's I, which is plotted up here. Remember, this is a complex plane. So this is 1 unit up on the imaginary axis, so that's I, and then minus 1 here, and then minus I down here. So then we can make this even larger. How about 14? And now it looks like these lines are evenly distributed around the circle. Now to make this point a little bit clear, I want to make the plot look a little bit nicer. So one thing I'm going to do is make this a square plot. Okay, so that already looks a little bit nicer. And now what I think I would like to do is plot a circle around here. So you can see that these lie on the unit circle. So you might remember how to do that from a previous video. So we basically want to draw cosine of x by sine of x, and I'm going to set the color to be gray. So now what is x? X was angles in radians that go from 0 up to 2 pi. So let's say x equals numpy.linspace from 0 to 2 pi in, let's try 100 steps. Let's see how this looks. Oops, that's numpy.pi. Now, if you're a little bit confused about why I'm writing these 2 lines of code and how that produces a circle, you might want to go back and consult the video on plotting the unit circle. Okay, and then I also want to make this a little bit different. So how about a dashed line like this? Actually, no, I think it looks better just on its own. Okay, so this is pretty neat. It's starting to look a bit like a wagon wheel. And the interesting thing is that what the roots of unity are actually doing is finding evenly spaced lines that go all the way around the unit circle like this. So we can try this for, how about 7? So now it turns out that all 7 of these lines are equally far apart from each other. So that means if this were a pizza and you cut this into 7 slices, then using the 7 roots of unity will give you exactly equally spaced slices. The exercise for this video is to produce a picture that looks like this. And isn't this beautiful? I think this looks really nice. It has a bit of a kind of seashell, like Fibonacci kind of look to it. And the colors go from black to white. I just think this looks really beautiful. So how did I create this? Well, of course, I use the nth roots of unity. And then there's one tiny addition to the formula that you've been working with. So actually, let me just make sure this is really clear. So I generated this plot by taking a formula that looks something like this, except I modified it somehow. Now, if you would like to figure out how I modified it and basically produce this plot on your own without me giving you any hints, then now is your last opportunity to pause the video. I am about to give you a hint. The hint is exactly the formula that you need to apply to get this thing to look like this. Okay, so here is the hint. Essentially, all you do is you take this exact same k number here, and you also multiply the entire expression by k. So now k is this extra multiplicative term in front of the exponent. All right, so if you needed that hint, then now you can pause the video and go back and keep working on Python. Now I am going to switch to Python and show you my solution. And let's see, I think I will start with, I'm going to put this in a new cell, but I'm going to start with this same code because it's going to look pretty similar. So what we need to do is multiply by k outside here, and let's already see how this looks. Okay, so this, you can kind of see it's going in the right direction. The lines are spinning around and they're getting longer as they go around. And let's see, let's get rid of this. And I'm also going to turn off the axis, so axis off. Okay, so this is looking a little bit better. Let's try n equals, how about 50? All right, now this is starting to look a bit like a colorful seashell. I'm going to set this even higher to 200. All right, looking better. I want to make this line a little bit thicker, so I'm going to say line width equals 2. Okay, so now this is almost done except for the color. So the way that I went about specifying this color is to start from black and then go up to not exactly white. If you go up to exactly white, it gets invisible because the background is white. So the way that I solved this is, actually, let me show you a kind of simpler way. So you could write something like this, color equals, and then in a list, you could say k divided by n, k divided by n, and k divided by n. Now this kind of works. It does start black and it gets lighter and lighter. And maybe you think it looks better this way because it fades smoothly into, this sort of white ether of non-existence. But I actually prefer it to stop when it's still gray, so I get a clear horizontal line here. So again, that is just my personal preference. So I'm going to create a variable that goes from linspace. It goes from 0 up to 0.9 in n steps. And so that means that here this ends up being color. So the kth element of color, kth element of color, and the kth element of color. So now you can see that stops when it's still gray. And if you want it to be more gray, you could set this to be, for example, 0.3. And now that one doesn't look really good. But anyway, you get the idea. Of course, you are welcome to play around with these colors. It's pretty interesting to see what you can do. For example, if you would fix the green value to be 3, then you get one that starts black and then it goes into this kind of dark purple into a kind of lavenderish purple. The very last thing I would like to point out in this video is that sometimes things can get a little bit confusing with variable names and property names, because notice I set this variable, this vector, to be color, but then I used it in here right after color. So this color here is a keyword that the plot function is looking for, and I called the variable name color as well. Now I have to say, I generally don't recommend setting your variables to be names that are also properties. It can be a little bit confusing for exactly this reason. And that's why I showed it to you. All right, this was a really fun video for me to make. I hope you enjoyed it as well. You learned about the roots of Unity and you learned to make beautiful plots in Python.